Hey, how about a race? Let's show what our vintage hardware and software can do on the track. The track in this case is to implement a simple program, no more than maybe 20 lines in BASIC. Theoretically, you can implement it in anything though. I'm going to put up some samples, and then I'm going to post some sample times, and I'll do my times using just interpreted languages. You can use anything you fancy. Shouldn't be too hard to beat the samples. The race isn't just about who's the fastest or the slowest. It's a chance to explore our toy boxes and do a show and tell. Maybe you can dazzle us with your coding by outrunning a mainframe running BASIC using a carefully crafted assembly routine on a Spectrum. It's all to play for. I'll group similar results together, and what I'd love to see is some competing entries from like a vintage PC or some 8-bit home computers. We'll put up some weighted performance indexes too, so just enter any old thing, or even any new thing. It should only take a couple of minutes. Here's our racetrack. We're going to write a short program. It approximates pi using a converging method. We'll use the Leibnitz series, which here's a link to Wikipedia. So now what happens is you divide 4 by an incrementing series of odd integers. You alternately add, then subtract the result from the current estimate. For instance, your estimated number equals 4 over 1 minus 4 over 3 plus 4 over 5 minus 4 over 7, and so on toward infinity. To reach every additional digit of pi, it gets exponentially more costly to calculate, but the program requires almost no memory, and it has no graphics and no I/O, so this is a real test of single-threaded CPU performance. Your finish line is to reach the maximum number of digits that you can within 5 minutes. The faster the machine, the higher the precision, but there's a catch. The higher the number of places you try to reach, the bigger the data types you'll have to use to avoid accumulating error. Up to 3 digits, you can use like a standard 32-bit floating point number, but to go up to 6 places, you're going to need to use a double or a 64-bit floating point number. Now, that will slow you down significantly, but if you have the horsepower, you can just keep going with higher and higher precision variables. I'll validate the results against a minimum value for each last dividing factor. There should be a minimum required for each digit of precision. Here's my vintage example. This is my Hewlett-Packard 9825B. It's a real computer, although Hewlett-Packard originally sold it labeled as a desktop calculator. They started selling these in 1977 as the 9825A, about the same time as the Apple II came out. What's inside is a mini computer processor designed in the mid-1960s but downsized to fit into 3 chips all in one package. It's a 16-bit architecture, unlike the Apple II or other contemporaries of the microcomputer boom. The clock is set at about 6 MHz, but would you believe it's adjustable? There's a little trim pot and a whole section of the service manual dedicated to setting it. The Beige-o-Vision machine gets a total of 62 kilobytes of RAM. About half of that is address space for the ROMs. The ROMs are all RAM mapped, and the ROMs on the B include a revised operating system and some extensions over the original A. As you can see, it only has an LED display, but it does have a built-in high-speed digital cassette drive. It's also got a handy thermal printer, and it has, most importantly of all, a 3-slot system bus that allows you to add things like the HPIB bus adapter. Now, with that, you can talk to all kinds of technical instruments, and storage devices, and printers, and whatever else. The 9825 is one of a very few systems that ever used HPL. That's Hewlett-Packard's own programming language. Here's what our racetrack program looks like in HPL. As you can see, it's a bit like BASIC, but it has far fewer vowels and a couple of other little quirks. For instance, look at the variable assignments. The syntax is reversed. Like many implementations of BASIC, HPL is an interpreted language. You don't get the full horsepower of the machine because it has to map between tokens and routines under the covers. The language creates a limit as to how far we can go with this particular program. In HPL, there's only one numeric type, which is roughly equivalent to a 64-bit double precision floating point variable. Now that means that I can only safely try for up to about 6 digits before accumulated error makes my result invalid. Under our race rules, the question is whether I can do that in 5 minutes or under. And I'm afraid the result is no. For my run, I got as far as 4 digits precision. The single-digit lap took about 80 milliseconds. 2 digits took 520 milliseconds, 3 was 9 seconds and 240 milliseconds, and then it took 1 minute and 120 milliseconds to complete 4 digits of precision. Realistically, you can disregard the first 2 runs as video timecode used for timing, based on just a beep or a change in display, won't be very accurate. we'll keep the 3- and 4-digit lap results as our vintage system baseline. Our second pacer lap is a modern smartphone. It's the other end of the performance spectrum. We're using my 2015 Fairphone 2. Inside this thing is a quad-core Qualcomm Crate 400. There's a mouthful. That's an ARM processor clocked as high as 2.26 gigahertz. It's got 2 gigabytes of RAM and runs Android 5.1. This time we'll be using Python, and I'm running this on PyDroid. Here's my sample application. It's basically the same as the one I'd written for HPL. I've added an internal stopwatch timing to it since the language and the machine support it. And I've used the decimal data type, which allows at least 80-bit precision. When I run it, here's what I get. For 1 decimal place, I get 0.37 seconds, so that's 37 milliseconds. For 2, it's 0.86. At 3, we're now just over a second at 1.056. Then at 4, we're up to 6.488. And my last and best run is going to be 5 digits at 81 seconds, 361 milliseconds. I know you can beat that just by lowering your precision a bit, but the way I've left the program, I could get quite a few more digits out of it. Now it's your turn. Use the sample code I've put in the comments and on the Facebook page, tweak it or write something completely new, any language you like. Video your run, share your video to YouTube or Facebook, then put up the time, maximum value of the dividing factor, your last estimate of pi, and your program listing. Put that all in your video or in your comments. While we're watching your lap, do some show and tell. Tell us all about what you've done and what you're running it on. I'll try and keep up with posting a leaderboard of results. I'm really looking forward to seeing how other people tackle this challenge. So off you go. Post your videos and look forward to seeing you back here.